In today's video, we're going to get started with all the parts that belong to Parts Group Section 11210 for a 1990 to 1992.5 6-bolt 4G63 engine. Section 11210 is the rotating assembly. More than anything, I want to just start playing with this rod balancer, but I can't do that yet. The engine requires some degree of assembly first, and my rotating assembly parts don't even live in the clean room yet. I haven't even torqued the mains. My block is actually fitted for a different crankshaft than what's going in it. Because my crankshaft selection has changed, my entire blueprint is a complete reset. So if I ever want to get around to using this balancer without wasting all my time, then all that other stuff has to be sorted out first. If you're going to balance your own rotating assembly, all of the parts in the assembly must be finished, fitted, and as clean as you can possibly get them before you start balancing anything. So that's what I'm going to do first. These pistons were the ones that were in the GSX's old 7-bolt block that consumed a pair of rod bearings. They're 20 overbore JE 9-to-1 compression pistons. They were already cleaned up and inspected by a machine shop. I'm cleaning them the exact same way as I demonstrated for the Hyundai build, breaking off a piece of an old ring and scraping out all the ring grooves. There's still carbon in the fly cuts, as you can see, and the solvent I use makes extremely short work of it. There was a lot of carbon. This is tedious, and you just basically have to keep repeating the same thing over and over again until the solvent flows clean and everything's washed away. I don't really care if parts of the pistons are slightly discolored, but everything stuck to them has to be gone before these go through their next steps. The wrist pins get the same treatment. I checked them before the camera started rolling and they all felt pretty okay, but some of them still need some work. These are full floating wrist pins, so they need to move freely. These pins have already been matched up with the piston, and after all they've been through, I'm going to keep them paired together for the rest of their lives. This will limit my options later in this video, but I'll explain that once I get there. After the number 1 piston was completely free of foreign material, and after the wrist pin proved that it fit properly, it went right into the clean room for safekeeping. Same thing happened to number 2. Number 1 and 2 didn't see a whole lot of abuse. It was the 3 and 4 rod bearings that fragged, so I sort of expected this. Number 2 cleaned up real easy. Wrist pin fit like a glove, and away it goes. Number 3 is the one that saw the most abuse on the old 7-bolt. Everyone's seen the engine come apart in the video already and knows that I don't hold back any info. It's pretty honest around here. The wrist pin was good and stuck in there, and I have a simple trick to address this. Once I got it out, I noticed that there was still some material ground into the face of the wrist pin. Bearing material is a fraction of the hardness of the wrist pin though, so I simply used some liquid metal polish to remove it. It's abrasive enough to take the edges off of any scratches, and it's also a good mechanical means to scrub anything that generally shouldn't be there off of it. It didn't take a whole lot of effort to restore the wrist pin to usable condition. But still, I don't want any of this metal polish residue left behind, so it gets washed again with solvents and wiped clean. We talked about looking every part over with both your hands and your eyes. Sometimes you feel things with your hands that your eyes can't see. Ultimately, it's the assembler's responsibility to discover and remedy anything unusual before it's all sealed up and put back into use. Cleaning isn't just about eliminating foreign material. Cleaning isn't a sign of OCD or of mental coping deficiencies. Cleaning parts meticulously exposes the problems and defects that can cost you thousands of dollars in lost investment the first time you turn that key. It's the most critical phase of your quality control. I'm wearing organic filtration and working with an exhaust fan running because I know that working with these solvents can be hazardous, and that I'll be in here for however long it takes to have these parts back in the best possible condition for assembly that I can put them in. Using proper safety gear will give you the endurance to survive this kind of chemical exposure and still do a good job. And wouldn't you know it, I find another thing that's going to take even more time in here doing this. While wiping down the ring grooves, I felt the rag snag something between the crown and the top of the compression ring groove, and that's never supposed to happen. I didn't see it. The machinist who gave these pistons a clean bill of health didn't see it either. I don't fault them for that because I didn't pay them to assemble this engine now, did I? No. I didn't want them to have all the fun. But here it is, right here. Apparently a chunk of bearing material that made it past the rings ended up getting sandwiched between the quench area of the cylinder head and the face of the hot piston. It hammered an equal-sized piece of the piston out the side of the edge of the crown, and that's unfortunate. Unfortunate, but not a deal breaker for using these pistons if I can fix it. All I did to fix this was fold a piece of 400 grit sandpaper over a razor blade for rigidity because I didn't trust myself here with using a file. If I slipped or missed or misjudged my angle of attack once or twice, I won't hurt the part doing it this way because this barely removes any material at all. I took every effort to only sand the lump back down even with the rest of the part. 400 grit doesn't leave a very smooth surface behind though. I could have used higher grits to knock it down, but the pistons are soft enough that I just used some liquid metal polish to smooth things over. The metal polish also removed embedded materials and fine scratches from the skirts, and just like with the wrist pins, I don't want any of this gritty abrasive metal polish or sandpaper bits on the part, so it gets fully cleaned all over again. You see, this is a pattern. The assembler's responsibility is the greatest point that I could demonstrate here. It reinforces the point in the previous video about checking behind where others have worked. My machine shop was not wrong to tell me that these pistons could be reused. Had this divot occurred near the fly cuts, then maybe I would have cursed, thrown in the towel, bought a new set of pistons, and be forced to rework the engine block's bores to fit them. But it happened on the thick outside edge of the quench area, where heat is less of a factor that could lead to hot spots cracking or melting it. This piston took a long time. I spent an hour on this one piston. It was not suitable for reuse when I started with it, but it is now. That's why I took 3 whole minutes of this video showing you this. I'm satisfied with how this turned out. Moving on. Number 4 was more of the same. No divot, but I had to polish the wrist pin because it experienced the same bath of bearing chunks that number 3 did. And that concludes the piston cleanup. We'll measure these and fit them in the bores later, then we'll balance all of this stuff, and that involves these rings and connecting rods, which I have, which we could do right now. But I'm going to work on the block and the crankshaft first before we get into the balancing part. The reason I didn't torque the mains in the last video is because I have to fit the main girdle and test fit several components first. The main studs are dry, and these ARP studs require ARP moly lube in order for the torque specifications to provide proper loading and stretch. You're not supposed to slather this stuff all over the studs and fasteners. That doesn't help you. You just want to lube the outer threads where the fasteners actually do their jobs. So I used an old clean main bolt to apply the moly lube inside the threads of the studs. With that out of the way, I reinstalled the main caps and ran all the fasteners down by hand. You'll see the gaps close where the edges of the main caps interference fit down inside the block. The reason I always assemble engine parts by hand is because it's another stage of feeling the condition of your fasteners. My preparations have been good so far because I didn't have any problems that required a closer look. But another reason I'm running this stuff down by hand is because the bearing girdle has fingers on it. It's made of rigid steel. If I put the bearing girdle on top of this and then I try to drive all the main caps down to close that gap, then I stand a chance of bending one of those fingers and introducing a load on the mains that could actually pull them out of alignment. So that's why I did this without the girdle first. Once they were all snugged, removed, and then the girdle was installed, it's important to check the stud installation depth. You want them all to be even. You'll want about 1 to 1.5 threads protruding above the nuts before you begin your torque sequence. It can take a bit of time to get the results that you're looking for, but the reason you do this is to keep the bolt stretch even across all 10 holes. If you're using the right thread lubricant and the other end of the studs are in clean dry holes, then they should stay in place as you complete your torque procedure. Installing ARP 10mm main studs with ARP moly lube requires a 3-stage torque procedure in even steps to 60 foot-pounds, so 20, 40, 60. I'm doing this on my workbench instead of on an engine stand right now because it makes the rest of what I have to do in a minute a little bit easier on my back, and a lot easier to film once this is finished. I'm using a torque wrench that doesn't just click when the torque setting is exceeded. I'm using a torque wrench that lets me see exactly how much torque was applied to each bolt after I've torqued it. Use a torque method that brings the pressure up smoothly and gradually in one single sweep. So leave yourself enough room to do this comfortably, however you have to do it. I've got all 10 of these fasteners within less than a half pound over 60 foot-pounds. Not sure if I could have done that better on an engine stand or not, but that's a great foundation on which to take my measurements off the main bores. Once you've finished, recheck all of your stud installation depths with the straight edge again to make sure that they didn't move. And it looks like I'm fine. Now for the crankshaft. This crank traveled halfway across the US nearly a decade ago. Based on the view counter, Rob's been thanked over 1 million times because I think I said it like 6 or 7 times in the voiceovers, And those videos collectively have 500,000 views now, so Rob, thanks a million now, literally. It's still not enough gratitude because all of you know this crankshaft is really fun to look at. It's been oiled and stretch wrapped for nearly a decade. The last thing that happened to it before it received that treatment was getting it repolished and taking a ride on a crank balancer. I'll link that video in the description for all the newcomers to the channel. I'm going to clean it up for assembly and then we'll take some measurements to see if it's going to fit inside my block with a set of standard 6-bolt main bearings. This crankshaft's already been pressure washed, but it's always a good idea to run a wire brush through all the oil holes. I'm not going to attempt knocking the plugs out to clean the inside of this thing out because there's so little material around the plugs that it could turn out badly for this perfectly balanced crankshaft that's now going into my clean room. To figure out if this crankshaft even fits the hole, first you'll need to measure all of your crank journals. For as little as $200 you can buy a quality 0 to 4 inch set of micrometers accurate enough to do this job. This Fowler set offers more than enough accuracy and resolution for the entire build. It's important to clean your micrometers and check your 0 points before you begin. There are actually 2 0 marks on each one on each side of the sleeve. If you need to make adjustments, just use the included spanner wrenches and references. Place the micrometer on the outside edges of the journal. Ratcheting thimbles are nice because it limits the clamping force and it helps make your measurements more consistent. There's a lock lever that you should set before you even remove it from the part. This is the 2 to 3 inch micrometer. That means that the first digit before the decimal place is automatically going to be a 2. The numbers on the sleeve are tenths of an inch. Each hash mark between the tenths equals 25 thousandths of an inch. Those marks represent the 25 thousandths of an inch that are graduated all the way around the circumference of the thimble. Add the thimble and the hash mark thousandths together and then you've got your first 3 decimal places. The 10,000th decimal place is indicated around the sleeve. Wherever the marks on the sleeve and the thimble line up is the 10,000th decimal place. And you can see here that we've got a 7, so 2.2437. Write it down. Repeat this procedure on all of your main journals. On the number 2 journal, we've got 2.225 plus 15 thousandths plus 1, 2, 3 more thousandths before the 0 is 2.243. And on the sleeve, it looks like we've got a 6. 2.2436. Pretty good so far. Here comes the thrust main, number 3. Unlock. Spin the thimble counterclockwise, position the mic, spin the thimble clockwise, and BAM! More of the same, 2.225 plus 15 plus 3 thousandths, and the 10,000th spot gets to be a 6 again. That's fantastic. Keep it rolling. On number 4, we've got 2.2436. Heck yeah, I've got 3 of a kind now. This is turning into a great hand. And finally, the number 5 main. 2.243. Oh, it's a 3. So 2.2433. I've got 3 of a kind. The crank that I was going to use on this car, which is the crank that ended up in the Hyundai, that thing was way more inconsistent than this one. Now I'm going to use the 1 to 2 inch micrometer on the rod journals. We get to practice with a different number now. We've got a 1 with a 7. Counting 1, 2 hash marks. Looks like we've got a 3rd, but if you look at the thimble, it hasn't made it all the way around past the 25 yet. Thimble's got 20 more thousandths on it, and then the 10,000th spot is going to be an 8. 1.7708. The number 2 rod journal, 1.77, and the next thousandths looks like it lines up right on the 0. Yep. You need to look at the mark straight on and centered, so 1.7710. Number 3 rod journal, 1.770, and it's an 8 again. Number 4, 1.7706. Well, even though some of these journals appear just to be a tiny, teeny little hair over the service limits, they're consistent and they're actually perfect for how I'm going to use this engine. That's the long and the short of it. This crank should fit provided I've got all the right holes for it. You'll need a tool like a dial bore gauge to measure the inside of the bore. You could use telescoping gauges if you have all day to work with them. I'm just going to set the micrometer off the journal for that bearing and then zero the bore gauge off of that measurement. The hole should be bigger than the crank, so the result on the dial bore gauge should be a negative value. However far the needle moves away from zero is your oil clearance. So if you want to know the measurement of the hole, it's crank journal plus oil clearance. Because there's an oil groove on the face of the block side of the bearing, make 2 measurements for each bearing, one on each side of the groove. They should be the same number, but if you look here, that's not what happened to me. I was pretty disappointed to see this. What I found was a smorgasbord of different values between 17 and 32 10,000ths of an inch, with several of the journals being tapered. This is not what's supposed to happen. The factory service manual states that there's a limit of 1/100th of a millimeter or 4 10,000ths of an inch out of roundness or taper. Frankly, I don't want any of it. But my bore measurements showed the mains are out of alignment and taper, and I didn't know why. I thought perhaps maybe somehow they got contaminated while waiting to be torqued. So I redid all the work you saw me do in the last video, cleaning parts and reinstalling them to ensure that nothing got trapped in the main journals or under the main bearings between the main caps or whatever. So I re-inspected, re-cleaned, reassembled, re-lubed, and re-calculated everything, re-snugged, re-torqued, re-measured, re-zeroed, re-measured again, only to discover the exact same results I got before it all started. At least I know my measuring devices are all accurate. So to rule out the possibility that it's my fault or the bearing's fault, I disassembled it again and tried the bearing swap trick with the big and the small journal measurements to see if I could find a different result after I re-inspected, re-cleaned, reassembled, re-lubed, re-torqued, and re-measured everything again. The numbers were once again consistently bad, so it's not me, it's not my tools, it's not the bearings, it's the block. So this thing's going to have to go back to the machine shop once we're done here. It's not the end of the world. This is a fixable problem. It just requires the right people and equipment that I don't have in my garage. What's unfortunate is that this is going to make a liar out of me. It doesn't look like we're going to be using that rod balancer after all. If the block has to get tweaked, then I'd better make sure the pistons fit right too. The process of measuring the bores for the pistons is the same, only the instruments have changed. First you zero your 3 to 4 inch micrometer to ensure that you're taking accurate measurements. Then I'm going to measure the piston a 1/2 inch below the long ends of the piston skirt and write that value down. You don't see me making a mistake right here, but I'm doing it. Oh boy am I doing it. Not once, but twice. You know that whole measure twice thing? You can measure twice and still make a mistake twice. The piston measured 3.3620. Now for number 2. I build procedures into my assembly to try to prevent errors, and you'll see me measure twice before demonstrating the result. I like to make my measurements repeat themselves before writing down or moving forward. 3.3623. Number 3, measure twice and get it to repeat. Looks like 3.3617. That's a 7. Come on, focus. Hopefully you can see that. Write it down, and we're on to the finishing stretch here. Number 4, measure until there's repetition. And there you have it, at 3.3622. Last number's a 2. So 3.3622, write that down. At this stage, I should have caught my earlier mistake. It should be jumping off the whiteboard and punching me in the eye and brain, but I'm distracted by how much memory card and battery I have left. This scene's not about to end, the memory card's just full now. Now that we have a new memory card and I know the piston diameters, we're going to measure the bores the same exact way that we did the mains. I started on number 4 because it was the last piston measured and the micrometer is already set to that piston measurement. You just take the distance that the needle travels from 0 as your piston to cylinder wall clearance. You should measure the full length of the bore where the rings make contact with it and understand that some taper is actually desired. Some of you are already typing comments about torque plates. Stop it. It's not important right now. We're just trying to see if the pistons fit. But anyway, next I set the bore gauge up for the number 3 measurement, and then look at what I do. I measure the number 2 hole again with it. Why, Jaffro? Why you gotta do that? I won't make excuses. Apparently I'm just gonna make mistakes. Humans have an unlimited capacity to make mistakes. It's a miracle that we've all managed to last this long, isn't it? I set the mic to 3.3610 like I wrote down on the whiteboard. And number 1 produced numbers even worse than number 3. It's at this stage where I questioned if I had the pistons for the right holes. And I do. But my numbers exposed 2 very human mistakes, despite measuring everything twice. On my first set of measurements, I cheated, and I paid for it too. When you've got a measurement that's really far off, reevaluate your entire process and keep measuring it to ensure that it's consistently wrong, because the problem might just be you. Where I failed, I set the micrometer to a previous measurement rather than remeasuring my part. Because I read the micrometer incorrectly and wrote the wrong measurement on the number 1 bore, I set my 0 point on the dial bore gauge to the wrong value. And it was off by that difference. Measuring twice won't ever fix that, and it won't stop you from measuring the wrong hole like I did on number 3. If you get weird numbers, you should always just go back over your entire measuring process, reset your zeros, and double check yourself, because the measurements are what they are. If you measure things 2 different ways and get 2 different results, then somewhere in your process it's broken. Fix it. Once my bandwidth shifted from accuracy and back to the fit, it looks like the pistons aren't going to fit either. They're too tight for how this engine will be used. They're even a tad too tight for this alloy, even for a non-turbo configuration. But I'm not mad at all about it. I got that out of my system when I discovered what was wrong with the mains. It's got to go back to the machine shop anyway. This is just something else that has to be done to it while it's there. Friction and performance don't mix, so when you're fitting your pistons, it's important that you follow the piston manufacturer's recommendations for your cylinder wall clearances, and not that value that's in your service manual. This would have actually been a little bit loose for what the service manual says to do for a stock build. In some cases, you have to go bigger because with more power comes more heat. You have to accommodate the properties of the piston material, and the piston's manufacturer usually knows what's best for them. So read your spec sheet, because some alloys grow more than others. In my case, I want to add 1.5 to 2 thousandths more hole on those recommended minimum clearance numbers to accommodate the extra heat that I plan to make, just like step 4 on that spec sheet said I should do. So 40 10,000ths clearance is what I want to see here, not 25. I'd really like to see it an extra 2 10,000ths of an inch bigger than that at the top, because that's where all the heat and the thermal expansion will be concentrated. The pistons aren't the only things that expand after all. Yeah, I know I missed a spot. Let's just get that out of the way. I don't want my machine shop to have to remove my oil squirters for me or to have to keep track of them in a busy shop, so out they go. Everything else can stay together though. They'll insist on taking their own measurements for the exact same reasons as you've witnessed here in this video. I mean, why should they trust my measurements? I'm sure that when I told them that these pistons were 20 over, that they thought I wanted 20 10,000ths more hole around each one, and they definitely nailed that for sure. But it's my fault for not handing them a spec sheet or being more specific about what I really wanted. I also can't expect them to be searching the internet when they should be running machines, dealing with customers, and answering phones. So this goes right back to the whole quality control discussion and about where I fit into it. Thermal expansion occurs at a rate of 6 millionths of an inch per inch of material per 1 degree Fahrenheit. It would take a temperature swing of over 34 degrees Fahrenheit to barely start to show up in the 10,000th spot. The factory specs are taken at 68 degrees, and they were not taken with a millionth of an inch accuracy. Sure, if you're outside in Nome, Alaska in January building an engine at 32 degrees below zero, then all your measurements will be 6 10,000ths of an inch short. You really don't need medical grade precision to get your oil clearances straight. Just do your best to set your clearances to spec at a temperature suitable for sustaining human life, and you'll be fine. You'll be close enough to those specs. I measured this today at 80 degrees, the parts are at 79 degrees, and it's 80 degrees outside. It's supposed to be 80 degrees all week. That means it'll be 80 degrees in the machine shop, because that's about all their air conditioning will do on a good day. It's a bit odd to me that the mains were this far out, and it's hard to pinpoint exactly why. The block did get baked twice to over 350 degrees, and it slowly cooled inside the ovens back down to room temperature. This shouldn't have warped it at all, but perhaps there is some stress in the casting that's relaxed. I don't know, this made me want to remeasure the deck of the block. It was milled previously to prepare it for an MLS gasket, and I'm expecting it to be perfectly flat. Using the 1.5 thousandths feeler gauge and a straight edge, I checked every single angle on the deck. I'm using a split it, box it, exit rule, and yes, indeed, the deck is flat. I can't get this feeler gauge under it anywhere. It's perfect. So the block didn't warp. Cool. I wasn't going to do this particular segment in this video, but this one just turned into more videos, and I've already got the parts to demonstrate this, so I might as well. Section 11210 is the complete rotating assembly. These are the factory part numbers for everything, but I'm not using much of any of this. You probably aren't either. My rings are JE Pro Seal rings, and there's the part number. Makes sense, I'm using JE pistons. Oh wait, I haven't gotten there yet. But there's the factory ring set measurements, and you'll see that they offer 5 different sets spanning fractions of a millimeter, which really just break down to standard 10 over, 20 over, 30 over, and 40 over. You get the size that matches your bore and your pistons. Let's be honest, nobody does this with the 4G6 Mitsubishi anything anymore. They just buy aftermarket pistons like I did and punch the block out to fit them. You already know my pistons and my wrist pins. For fans of the stock pistons and pressed-in pins, you can buy the piston assemblies in 5 different sizes, from standard to 40 thousandths overbore, using these part numbers. Instead of factory 6-bolt rods like what are in my Hyundai, I'm using these Manly Turbo Tough 6-bolt I-beam rods with 2nd generation DSM pin bores to accommodate my old 7-bolt pistons. These are the rods I bought for this build back in 2012, and this part number is specific to my equipment. But if you're a fan of factory rods, you could reference the complete assembly for 1G 6-bolt or 7-bolt using these part numbers. The ability to order rod bolts and nuts individually is pretty cool. It makes sense in a rebuild, and if you didn't need the whole assembly, the part numbers and specs are all right there for you. 8 quantity for either one if you need them all. Yes, the 6-bolt rod bolts are 9mm. Strange, isn't it? The rod bearings I'm using are ACL 4B11 46H standard race rod bearings. Rod bearing part number intensifies! You only get one part number whether you like it or not. Make it fit, I guess. I ran both 6 and 7 bolt VIN numbers through caps and got the same part number out of it, and I know that's wrong. My crankshaft doesn't look anything like the one that's in this drawing, but there's the part numbers for a 6-bolt or a 7-bolt crankshaft. The 6-bolt factory crank has been out of production for many years. The end of the crankshaft is milled out for a woodruff key, and there's its part number. It's just a metal half-moon thing with specific dimensions to fit down into a groove in the snout of the crankshaft. If the woodruff key gets lost or is damaged, fortunately you can still buy this part. I don't think mine's rough enough to warrant replacing it, but I do own 4 of these cars, so one of them might need it. Other pieces of the crankshaft flare include a washer. This is actually Evo part number MD377400. MD012455 doesn't exist anywhere anymore, so look for the Evo part. It can get bent over time like my old one did, so check yours and make sure it isn't concave. Crank pulley, 6-bolt or 7-bolt, it doesn't matter. These are interchangeable. They're also really expensive to replace. I'm not using those, but if yours blows up, the price difference justifies buying a better one. I'm using this fluid damper 630701. It offers a lot better damping of harmonic vibrations than the stock unit, but with a one-piece design that's not going to need replacement because the rubber thing came apart. I even have some crank pulley flare for that nice anodized crank pulley. I swapped out my crank pulley bolts with ARP chromollies, which are a total overkill here because these only see 18 foot-pounds of torque. There's nothing wrong with the factory bolts besides being ugly. But these mess me up because they have 10mm heads and I always grab the wrong size wrench. And of course, the crankshaft center bolt. I didn't get the ARP bolt because I refused to accept a 12-point head. Sure, it's better, but I'm not ever going to have that socket with me, so... There's the flex plate parts that look like stuff that came with my ceiling fan. There's the flywheel, which we're not going to talk about right now, but okay, fine. There's the flywheel bolts. Make note of those lengths between the automatic and the manual transmission 6 and 7-bolt cars, because it matters. Get it right. And oh yeah, the crankshaft dowel pin. Only all-wheel drive manual transmission cars got this part according to my documentation. Not sure that's correct, but it goes right there in that hole. If it can fall out of the crank on its own, then it's toast, and you need to replace it. If your crank doesn't have it, it didn't come from an all-wheel drive turbo car, or the last jerk who rebuilt it didn't put one in there. I'm of the opinion, if the documentation is incorrect, that all manual transmission cars need this part if they want their flywheel bolts to stay tight. That's the long and the short of 11210. You can clearly see what I'm opening here. This Map Performance torque plate is a work of art, and I'm really glad to have it. This adds hundreds of dollars to my build, but I can finally justify it because I own several of these engines. Now we can talk about torque plates. The Map Performance torque plate includes 10 steel spacers that spread the torque load evenly over an even larger clamping area. Use the exact same fasteners, lubricants, torque specs, and the procedure for installing your torque plate as you'd employ in your final assembly installing the head. I'll be testing the tensile strength limits of my ARP 207-4201 12mm head studs because I have no money left for L19s. They cost 3 times as much. This is a gasoline burning street strip build, so I'm not sure it'll see more than 40 psi. If that changes, then I'll deal with it later, but with the packaging oil cleaned off of all 10 of these things, they go into the block hand tight. You watched me chase and clean these head bolt threads in the last video. These studs are a snug fit when they're bone dry. A used flywheel bolt works beautifully to drive the head dowel pins into a 6-bolt engine because of their length and because it's the same thread. I don't know where you'd get an M11 by 125 bolt to do this for a 7-bolt dowel pin. I've used a plastic mallet in the past with some success. It's probably not the ideal way to do it, but at least I know it had nothing to do with why it blew up. A head gasket isn't necessary between the torque plate and the block, and you just ensure that both mating surfaces are spotlessly clean and set it right down against it. Next, install the spacers, or the load spreaders, or whatever you want to call them. You get the idea. Lubricate all the threads. Install the washers and nuts. And follow the included instructions for torquing your head studs. These get a 3-stage torque procedure in even steps, so 30, 60, 90 foot-pounds. The only time a torque plate really matters is when you're boring and honing the block. That's it. An engine can be bored, honed, and blueprinted without a torque plate and it'll still turn out just fine. It may not be perfect, but it's going to perform close to its maximum potential if you do everything else right. If you did your machining with a torque plate, then the hole is round, and any measured variations that you find at home are meaningless because the machines don't punch oval-shaped holes. Those values will almost certainly fall within spec once it's torqued down, so long as your head's not warped. So if you know that a torque plate was used, then you have nothing to worry about if you detect flaws in your measurements. My machine shop has a 4G63 torque plate, and this is why you've never seen one in my videos before. I'm not going to tell you that they're unnecessary. If you need perfection, then ask your machinist if they have the torque plate for your engine before you hire them to perform this kind of work. Aside from the block, I just need my crankshaft and my pistons. Bearings are in the block. The block is in the truck. I'm going to wrap the crank in stretch wrap to keep it clean. They might appreciate that. The pistons are in a drawer. I need a box for those. It's a good thing I just unboxed the rod balancer because this is perfect. Bubble wrap and everything. They close in 45 minutes. Now go on, get! As long as you're expecting that everything that can go wrong will, then nothing about assembling an engine will ever get under your skin. The bores being wrong is my fault, and I can own that, but the mains, I can't explain. You've seen everything this block's been through, and it could have been the twice-baked finishes or the previous line-hone job, but I'm not pointing fingers. You overcome problems by owning them, even if you can't explain them. So let me be the living example that baked finishes should be performed prior to doing your machine work. Now I've owned it, let's fix it. Alright, we're there. I have a great relationship with my machine shop. They're some of the hardest working people I know. As busy as they stay, it's always a gift when they let me inconvenience them with any of my camera equipment. It would be cool to bring you some footage of how we get this resolved, and maybe if I get lucky we'll get a chance to see that. I have to give birth to this video though before I can get pregnant with the next one. So in the meantime, be sure to check out the description for more information and references, and thanks for taking an inside look at my quality control. Most of all, special thanks to everyone on Patreon supporting my production. I couldn't make these kinds of videos without you, and you're all helping to make YouTube a better place. Be sure to pick whichever thumb suits you best and leave a comment, and, maybe subscribe if you're new here. But until next time, stay tubed.